Uh, I'll preface my talk by apologizing for not being able to be there. We would love to be in Seattle. It's some complications, at least on my part. So I'll start. So I'll talk about this work that is ongoing. We aim to give a fully abstract operational game semantics model for language with algebraic effects and effect handlers, which has the capability of dynamically generating effects. Uh, so my name is Hamza Jaâfar, and this is a joint work with my advisor, Guilhem Jaâfar. I'll start with an introduction, a bit of history of the origins of algebraic effects and handlers. They appeared in the work of Plotkin and Power in the with the aim to give the notational semantics for impure behavior. And in this setting, impure behavior is given by arises from a set of operations that act on computations. And one can think of operators like choose or for non-determinism, raise for exceptions, set and get for global states and whatnot. And this behavior is described by an equational theory on these operations, yielding an algebraic theory of effects. Since every algebraic theory, like to each every algebraic theory corresponds a monad, then they can account for multiple monadic effects, specifically those whose operational behavior is independent of the context in which they are evaluated. Here I'll give just an example of a choice operator for non-determinism, and we see that is independent because the evaluation context and the operation itself can permute. So the permutation property is satisfied. The advantage they give us over maybe monadic effects is the fact that they are easier to structure effects, so they give us more modularity and easier to combine. And in this setting, very algebraic setting, handlers arise as homomorphism between free models to other models given by the property of free algebras. But since we're interested in a more operational view, we will depart a bit from this algebraic origin and look at the related notion of programming with effect handlers. In this setting, we have in our language a set of operations that could be seen as constructors of effects and effect handlers that are destructors of effects. In a sense, they generalize exception handlers, a generalization in the sense that we do not only have access to the exception or the effect in question, but we also have access to the limited continuation. We can do something with it. So more concretely, we'll have a language to which we add a lot of operations given by arities, that is functional-like operations. Here we can read it as an operation takes as a parameter a value of type tau and is supposed to return something of type sigma. So performing an effect amounts to using this symbol with a value of type tau. Handling an effect, well, since handlers are evaluation context, there are two cases. Either the enclosed computations returns a value, then this one, as we see here, will be bound to X, then used in N. And in the other case, if the computations performs an effect, then we bind the parameter to P, and here kappa, to which we bind the limited continuation. And then we handle it as we wish. So effects are in general will be given by their signatures, which is just a set of operations that they involve with their respective arities. So for example, if we want to do global state in which we want to store something of value of type tau, we would have a set and get with their appropriate type like this. But the thing is, what if we want multiple states that hold the same value? We could have more symbols like set1, set2, and their corresponding get1 and get2, but we lose a bit of modularity. So more general, how we deal with multiple occurrences with the same effect without giving up modularity. For this, in our language, we will follow the approach of the F experimental language in which each instance or occurrence of an effect, we associate a distinct identifier, an instance that we here name iota. So similarly, if we want to perform an effect or handle an effect, we just use the operational symbol op as denoted here in conjunction with a specific instance. So as I said in the beginning, we're interested in dynamic generation of effects. So we need a constructor to do this generation. Again, similarly, we would follow the approach of F. And we add to our language a constructor called new with a signature of type E that will create a fresh instance of this effect E. The operational semantics will be standard. It's just a relation over this pair, a term and a store that is supposed to hold all the instances that have been generated so far. So the standard way to deal with generation of fresh names in general. So since we have this phenomenon that is local, we have instances have, with respect to the environment, a status. They can either be private or public. So for example, an instance could be generated and remain private. I'll give here a simple example. Here we have, in this example, the way we did, we create a new instance, we bind it to X, then we do something with it inside the handler. Here we perform the effect, the operation, the effect E by using the operation op. But we could also disclose it to the environment. Disclosure is either by returning it as a value or passing it to a function that belongs to the environment. Here we give an example. Here is a simple example, just we create a fresh instance and we pass it to F, which belongs to the environment. And well, yes, here I gave an example, but it could be anything of a context. Here just binds it to, well, it takes it and does effectful operations with it. So now that we laid out the essential bricks for our programming language, I'll try to give a more or less formal definition of our language, which is basically fine-grained, call by value, which is essentially we have a distinction between values and computations, and a call by value strategy. I start with the syntax of types. We have value types and computational types. Value types would have like functional values, records, variants, and effect types. For computation types, here like tau, bang, delta, and they just say that the computation is supposed to return a value of type tau, and delta is the set of operations that it could trigger or perform during evaluation. The syntax of terms is again standard with nothing worth detailing. I highlight in blue everything that deals with effects and generation of instances of effects. And of course, evaluation context, which makes our language a call by value language. So for the operational semantics, the new constructor, as we already went through, is standard. For the handle case, if the enclosed continuation returns a V, we look in the handler for the return case. We substitute V for X in M. In the other hand, if the enclosed computation triggers an effect, what we'll do is just again we'll look in the handler definition. We substitute for X the value V, which is the parameter, and we substitute for the kappa, the delimited continuation, which is here given by the evaluation context E prime. Plus, we wrap it around the same handler. This way, it gives us the standard deep handlers. And we're interested in looking up some equivalences between programs. So it's I'll give what type of contextual equivalence that we are considering. Here we just observe termination. A term terminates if and only if, when evaluated, it returns a value. And the contextual equivalence, this is just a rough, not a very precise, but the idea is that if two terms are contextually equivalent, if we plug them in the same compatible context, here C, then either they will both terminate or none of them will terminate. So this is now we'll look more concretely to some examples. Here I'll look at this very simple example. We have an open term, f, which is a free variable, and we apply it to the constant function that returns the value 5. Now let me convince you that this term is equivalent to this other term. Let's look closely to what this other term does. We start by creating a new instance. We bind it to y. Then within a handler, we apply f to, again, somewhat of a constant function that the only thing that it does, it just triggers an effect or performs an effect with the same instance that is bound to y. And what the handler wrapped around it does is that it captures the continuation. Whenever it captures this effect with the same instance, it will pass the value 5 to the continuation. Well, we can think of a lot of scenarios, but the one that are interesting is when f doesn't use its argument, then we can see that the behavior is prescribed by f, so they both behave similarly. In the other case, if f uses its argument, then for the first term, it will try to evaluate the constant function. It will return 5 to it, then it will continue. In the other one, it will try to evaluate its argument, which is the one that triggers the effect. It cannot handle the effect, so its continuation will be captured by the handler, and to this continuation, as we see in the handler, will be passed the value 5, and then we continue. So we'll see in either case whether it receives 5 and it continues, or whether the handler captures its continuation and passes 5 to it, the result is always the same. But this holds only because the instance has remained private. Now, what if we change it a little bit and we now disclose this instance? It's a bit similar. We create an instance, we disclose it through this function g, as we pass it to this argument, and we do the same thing. Now, if we try to do the same thing to the constant function, it will not be contextually equivalent. Because, well, I'll not give a discriminating context, but one can think that a context that has the capability of doing effects, it could be stateful. So in the definition of G, it will store the instance, and in F, he could use it to use a handler. This way, he will discriminate between a function that triggers an effect and a function that does not. So in our model, we'd like to capture such equivalences. So before going to models, I'll briefly say what are models and recall what is the definition of a fully abstract model. Model is nothing but a semantic domain and interpretation from this language L that comes with this operational semantics to this semantic domain. And if we have an equality on this semantic domain, the property of being fully abstract just means that our equality in the semantic domain is sound and complete with respect to contextual equivalence, the meaning that the two equivalences coincide. In other terms, M and N, or two terms, are contextually equivalent if and only if their denotation are equal. So in terms of what is already existing in the literature for models for effect handlers, there are a lot of sound models, fully abstract models. There's a main, as far as I know, there's the one of the only ones that are complete, and it's the model by Biernatsky and co-authors, which is based on Lassen's normal form by simulation, and where we depart from where what we have as dissimilarities between their approach. Well, they work on an untyped calculus, and they have a set of global operations, and we try to tackle a calculus that is typed, and plus we have this disclosure and generativity. Usually in these models, completeness is achieved with some form of state, and they manage to do it only with effect handlers, and we hope to do the same. So, but it seems that such B-simulations cannot be easily, or at least not directly, extended in the presence of generativity and local names for similar reasons as applicative B-simulations fall short. So now our model is operational game semantics model. So I'll try to explain what it is. It's basically where a program is considered a player called a proponent, and its environment is another player called opponent. And it's essentially trace semantics that traces their interaction. And yes, and so it gives us a lot of traces, and these traces are sequences of moves, P moves, player moves, and opponent moves, which can be seen as a sequences of calls and returns. So questions could be of the form F applied to A in C, which can be read as we're requesting the result of F applied to A in the continuation named C, or an answer, just replying in a continuation name with a value E or A. So I'll try to give the intuition by following an example. We go to the example that we've seen before, and now we try to see how it interacts with the context in which we bind to F the function that takes as argument a function, applies it to value, discards the result, and returns true. It's a normal form. It cannot be evaluated, so the only thing is to ask a question on F. Apply to G. G here is the constant function. As we see, the environment will try to apply the function, yielding a question on this function named G. We know the function is the constant one, so it will reply with 5. We give control back to the environment, which will give us true. This is how generally this is the way these traces are constructed. But generally, as we see, like the idea is that normal forms are some form of the interaction interface. So now we have, given our strategy, we have some normal forms. So for example, if the normal form is because we're stuck, because we cannot apply a function, it calls for a question on F. If we have a return, then it's an answer, or a return in the trace. And given a term M, if we look at all its possible interactions with all its possible environments, it will give us a set of traces, and this is what we use as a denotation for a program in our language, in our semantics. Now we need to add fx and handlers. So we follow the approach of normal forms being the interaction interface. They add a new component to the normal forms. So we need something to account for it. But interaction is something that is observable. But here the question is, what is observable, or what counts as observable? So let me explain. If a program performs an effect like this, operation and the instance iota with the parameter v, this iota instance could either be public or private. It has either been disclosed or not. So if it's public, the opponent could potentially handle the effect, making it an observable thing. If it's not, then the only thing that the opponent could do is just forward it. The same way an error could be propagated if there is no handler that will catch it. So now, having this in mind, we add new moves to our traces, which account for this. An observable effect, here we kind of mimic the normal form. It's a return. We give to opponent access to the effect that has been triggered, the parameter through the name A, and the delimited continuation through K. Here it's given in the normal form by the evaluation context E. If it's a private effect, then what we do is that the only thing that the opponent could do is just propagate it. But he will also need to propagate its continuation, because it is a fragment of the delimited continuation that could be used by player if there's a handler around the computation. So I'll go to something more concrete. Okay, we have a remember this trace, recall this trace of this term M1 that represented this interaction, and then recall that we said that this term is equivalent to this term M2, as we've seen. But now let's look at this term M2 when it interacts with the same environment. M2 evaluates to this normal form, then we look at the trace it generates. It starts by asking a question because it doesn't know what to do. Then opponent will try to evaluate it. So it will have a question on the trace. Because the instance is private, the only thing is forward move. Well, we capture the continuation, which was representing D. The handler will just pass 5 to it, giving control to the environment, and then we have true. What we see here is that two equivalent terms do not have the same denotation. So we need a coarser, we need traces are more of an intentional object. So we need a finer notion of trace equivalence to that will take this into account. So we need to relax the notion of trace equivalence. So the technical way of doing this, I'll quickly go over it. So we just have some canonical forms in which we remove forward moves that are not observable, and then we refine trace equivalence based on that, in the sense that the denotation of a term is more precise. It's no longer just set inclusion, but we only ask that there is in the other set a trace that is canonically equivalent. So just a way to refine. I will not go over this this definition because I'm out of time. So we'll get to the results. We have thus far proved that our model is sound, which means that the trace equivalence implies contextual equivalence. We thus far conjecture, but we firmly believe that is fully abstract. We still require to work out some technical lemmas regarding this equivalence and relaxed notion of trace, but we conjecture that contextual equivalence also applies the trace equivalence, the relaxed notion that we have just introduced. So in conclusion, what we have done is that when we see that when we add generativity of first-class effect instances to a language, contextual equivalence becomes more subtle, and we're trying to capture it with a operational game semantics model. So we had to extend the interaction interface for effects, then for private effects, and then we realized that the trace is what we have, that the trace is too intentional, so we need to find something that is relaxed and coarser in order that the trace equivalence coincides with the contextual one. Yes, thank you. And if you have any questions.
I don't know if you could hear, but we all clapped. Thank you for the nice talk. Are there any questions from the audience first? Well, wait, I have a question. Oh, so first I just had a very simple technical question, which was you said that your notion of observation was non-termination, but you went through too fast through the language, so I didn't see why you actually did have non-termination in the language.
We could have a recursion through the let binders, and I also think we have maybe we didn't add it in the syntax, but we could have recursion in functions definitions.
Well, I didn't know if you used Landon's not or something cool like
Yeah.
that. Oh, and another question I had was about this equivalence you showed using the freshness of the name that you couldn't catch the effect because the name was fresh. Could you go back to that example?
Okay, you want me to go back to a specific?
Yeah. So the first time you showed this F. The example where you relied on the fact that you couldn't catch it. Yeah, this one. Okay. So yeah, so this
Okay.
one works because F can't catch Y, right? Because it's fresh.
Yes.
But in a lot of languages, you'll have, for example, a finally block after an exception handler, or you might have a catch-all case for an effect handler. So that would make these no longer equivalent. Is that correct?
Yes, that is correct. We don't have the catch-all for
Right.
here for
Yeah.
yes.
But so those features are very important, though, right? When you have resource management in the language, right? Because without having those kind of features, you can have resource leaks where, say, F allocated a resource, and then the function it was calling escapes, right? And then the resource is never recovered, right? It's never deallocated, right? So would there be a way that you could still have, are there other examples that would be where you can, you have interesting equivalences using this freshness, but you can still have some kind of a finally block like this?
Well, I don't think I have any examples as of yet.
Okay.
Because well, I think maybe at the beginning we just put this aside of having the catch-all because it kind of breaks this kind of equivalences, but it could be interesting thing to
Sure.
To see because
Yeah.
Maybe I can add just one more sentence. We could add a catch-all, and then it means that, I mean, we could relax the model in a way just by allowing like not doing the forward, but like doing a public kind of public action, like just forgetting about what is private. But the difficulty then is that with a catch-all, we need to be uniform so that when we perform a catch-all, we need to behave the same way with respect to all the private instances. Mm-hmm. And so to ensure this uniformity is really tricky. So in a way, we could see our work as a first step, trying to do the catch-all. The problem that with the catch-all, it's easy to be sound, but if we want to be complete, this is going to be really challenging because of how to enforce this uniformity condition. And so that's why, we try to simplify about the setting, a bit the setting without considering the catch-all.
Wait, so you're saying with a catch-all, it would actually be more complicated to make a fully abstract model? Really?
Yeah.
Okay. My intuition would be the opposite.
The sound is complete, but the completeness is
I think the
completeness.
It will be more tricky. Yeah.
Okay. Cool.
Can you hear me? Yes.
Yes.
I missed what the type system is here.
I'm sorry.
Do you have a type system here? I missed that part.
Yeah, I didn't give a type system. No, I didn't, not in the slides, but we consider it typed. I just gave the syntax.
Yeah.
Yes.
So what is the type system? Is it the same as the one? Well, the problem is F has several different versions.
Like what exactly the?
It's the one from the original paper, or from one of
Yes,
the
from
early
the
papers.
it's based mostly on the original paper.
Okay,
We add
okay.
things like records and variants, but it's very close to the original paper. Yes, the
Okay.
type system
Thank
is
you.
there.
Okay, great. So we can take any more questions on Discord afterwards. Thank you, Hamza.
Like, thank you.